It's an important topic from wave optics, the single slit diffraction. The experimental setup consists of a single slit, a screen with a hole. This is the screen. Slit is AB. Light rays are incident, normal to the plane of the slit. It's a plane wavefront, parallel light rays, normal to the slit. The width of the slit is AB, which is small letter A. A and B are the top and bottom points of the slit. C is the central point. This is screen placed at a distance capital D. OC is the perpendicular bisector to the screen and the slit, central line. The light rays entering through the slit. Some of the light rays can go straight. The lens can converge to the point O. Some of the light rays bending at different angles can be converged to different points on the screen. Now, Y represent the position of any bright or dark spot from the center of the pattern. I think the primary idea you have, like the diffraction is the bending of light around edges of obstacles or slit so that it creates dark bright pattern or bands on the region. Here we are going for just the explanation of the pattern, not going to the basic definition for diffraction. So the point P, any point P on the screen appear dark or bright with respect to the path difference of the light from the entire slit A, C, B, every point between AC and CB, the complete AB, the light rays reaching at B. The basic difference with the diffraction, we had just 2 point sources, so that every point of the screen was just receiving one light ray from slit 1 and another light ray from S2. We just want to discuss the superposition of 2 light rays at every point on the screen. But in a diffraction, every point on the screen receive light from each and every point of the slit. Means if this is a point P, light from A, light from just below A, light from below that, complete slit A to B, each point will send light to P. The P will appear bright or dark with respect to the total superposition of all these light rays reaching at P, waves reaching at P. So first we find the path difference. For that, take the top and bottom light rays. This is the top light ray reaching P. This is another light ray from the bottom parallel to that. So both of them have the same angle of deviation called diffraction, angle of diffraction. So this path is shorter than the path from B. So if you construct a 90-degree line, AN, BN represent the additional path traveled by the light ray from B to P compared to light from A to P. So BN is the path difference. So finding the path difference, we take sine theta from this triangle. So this angle of diffraction theta, this will be 90 degree. For example, if this is 30 degree, this section will be 60 degree. So to find the total intensity at every point on the screen, we need to find the total superposition of all the light rays from each and every point of the slit to a single point on the screen. We need to find the path difference. So finding the path difference, this is 30 degree. This angle will be 60 because it's 90. So this line AB and this dotted line are 90 degree. This is 60. This will be again 30. That means angle BAN will be same as theta. So finding sine theta, opposite side is BN. By hypotenuse is AB. This is 90 degree angle. So BN by A. Sine theta n is equal to Bn by A, width of the slit, or A sine theta equal to Bn, which is the path difference. So we got path difference. Now trying to explain the formation of pattern. If the theta is very small, practically theta will be 99% case will be very small. So that time we can take sine theta n as theta n. So the equation will become Bn, path difference, equal to A theta n instead of A sine theta n. That's a path difference. But when you use theta n for calculation, must be careful. The angle must be converted from degree into radian. Sine theta n, it's fine, but angles always used in calculation in radian. So angle will be converted into radian, multiplying with pi by 180. We are trying to explain the pattern formation for the central maximum. Central maximum is the pattern formed at O. So imagine light rays coming incident on the slit. Some of them are going straight. So for those light rays going straight, there is no bending away. The angle of diffraction will be 0. So theta n will be 0. Theta n is the deviation from the straight path. So theta n is 0. Path difference will be 0 for those light rays meeting at O. So the path difference 0 corresponding to constructive superposition. So the constructive superposition leads to the formation of a bright central maximum. 0 path difference, constructive superposition, bright central maximum. That's a point for formation of central maximum. Now there are other points on the screen which appear maxima or minima, bright or dark, as per the path difference. So if you try to explain secondary minimum, which is a dark band, for that we are trying to use a strategy. Minima means when the light rays get cancelled off. The explanation is easy. If you find light rays with path difference lambda by 2, so that lambda by 2 path difference is a condition for cancellation, destructive superposition. You don't want to count the intensity of those light rays. If all are lambda by 2, it will be totally dark. If some of them have path difference lambda by 2, those light rays get cancelled off. We have to count the intensity of the remaining part of the slit. So for this one, we imagine a point P, so that light from top of the slit A and bottom of the slit reach P with path difference lambda. The total path difference between A and B reaching P is lambda. Since we want lambda by 2 path difference for the explanation to get cancellation, imagine the whole slit AB divided into 2 half slits identical, AC and CP, so that the path difference becomes half when A becomes half. The total path difference for AB is lambda. So the path difference for AC will be lambda by 2. That means light from A and C reaching P will have a path difference lambda by 2 if A and B reaching P is lambda. So the light from A and C get cancelled because of destructive superposition. Not only that, every point below A to C, there's a corresponding point below C to B. so that light from these corresponding points, all of them, A to C and C to B corresponding points, light rays reach P with lambda by 2 path difference if A and C are lambda by 2. So complete AC section light rays have another counterpart light rays from C to B, all of them corresponding light rays reach with path difference lambda by 2 P. So complete intensity of AC is cancelled by light rays from C to B. So P will appear as a point of darkness or minimum. Now same is the case for another point P where the path difference is 2 lambda. So we imagine that to split into 4 identical sections. If you take 2 identical sections, total path difference 2 lambda becomes only lambda for AC and CB. If you imagine one more section AD and DC, CE and EB, AD will have lambda by 2 path difference because quarter slit will have quarter path difference. Total is 2 lambda, quarter of 2 lambda is lambda by 2. So light from A and D, which is midpoint of AC, on reaching P have a lambda by 2 path difference, they cancel off. So similarly, A to D and D to C have corresponding light rays with lambda by 2. CE and EB have light rays with lambda by 2 on reaching P. So again, the entire slit intensity will be 0 on the second point. So lambda, 2 lambda. Similar is the case for 3 lambda, 4 lambda, generally n lambda, where the slit can be divided into even number of half slits. For lambda, we divide into 2 lambda by 2s. For 2 lambda, we divide into 4 sections of lambda by 2s. 3 lambda, we divide 6 sections of lambda by 2s. So generally for n lambda, we divide 2n sections of lambda by 2. Each corresponding section light rays satisfy condition for destructive superposition and cancel off. So those points all appear dark or minimum. P, light from A and B reach P with lambda. So AC and BC corresponding points is lambda by 2. Destructive superposition dark. Same for 2 lambda, 3 lambda, 4 lambda. So generally n lambda where n equal to 1, 2, 3, not 0, and starting from 1, 2, 3 only. That's a condition for dark band or minima in diffraction. We already know delta we calculated as either A sin theta n or A theta n. So you can substitute that here. So A theta n equal to n lambda, or theta n will be n lambda by A is a condition for the dark band diffraction where n starts from 1, 2, 3. So we explained for lambda path difference point 2 lambda, 3 lambda. Now for the explanation of maximum bright region, take points midway between lambda and 2 lambda. Between lambda and 2 lambda, the midpoint is 1.5 lambda or 3 lambda by 2. So that itself tells us how many sections we should imagine. We should imagine in such a way each section have lambda by 2. So 3 lambda by 2, we imagine 3 identical sections for the slit. Out of the 3 identical sections, the first 2 sections corresponding points will have path difference lambda by 2, so that the first 2 sections of the slit, 1/3 sections of the slit gets cancelled off. The intensity on the screen is only due to the last 1/3 of the section, which is 1/3 of the intensity of the central maximum. So the total path difference between A and B, imagine to that point is 3 lambda by 2. Since we need lambda by 2 path difference for cancellation, we imagine the whole slit into 3 sections. Out of 3 sections, 2 corresponding sections get cancelled off because of destructive superposition. Intensity is only due to the 1/3 of the slit. That means the point P where 3 lambda by 2 path difference totally from A and B appear with the brightness 1/3 of the central maximum. 1/3 of the brightness of the central maximum. Now, similarly, if you take another section between 2 lambda and 3 lambda, that is 2.5 lambda, which is 5 lambda by 2. So imagine the whole slit to be 5 sections with lambda by 2 path difference. Out of that, 4 consecutive sections pairing, the intensity get cancelled off due to destructive superposition. The intensity on the screen will be only due to the 1/5 of the intensity of the central maximum. So same case for 5 lambda by 2, 7 lambda by 2 all will appear as 1/5 of the intensity of the central maximum, 1/7 of the intensity of the central maximum. For even pairs, the dark ones, there are equal number of even pairs get cancelled off, but odd number of pairs, or one section will be always left out. Out of 3, 2 cancel, 1 left out. Out of 5, 4 cancel, 1/5 will be left out. Out of 7 sections, 6 get cancelled, only 1/7 will be left out. So generally, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2 comes as 2n plus 1 lambda by 2 with n equal to 1, 2, 3. Putting n equal to 1, we get 3 lambda by 2. N equal to 2, we get 5 lambda by 2. So the path difference for formation of secondary maximum is 2n plus 1 lambda by 2 with n standing 1, 2, 3. No 0 here. Again, delta you can substitute as a theta n. So a theta n equal to n1 plus lambda by 2n plus 1 by into lambda by 2, or theta n is 2n plus 1 lambda by 2. This is the angular position. From here you can measure the angle from the center of the slit. You can measure the angle theta n. If you want distance from O to P, y, angle theta equal to arc length by radius. So theta is equal to y by d. Theta angle, if you take triangle CPO, very small angle, arc length y by capital D. Theta equal to y by d, or y is equal to theta into d. So y, the distance along the screen, can be obtained by multiplying theta with d. So y n for the minima will be d times of theta n, that will be d times of n lambda by a. It's not 2a, n lambda by a. Similarly, here we have d lambda by 2a. When you multiply theta n with capital D, so it will be 2n plus 1 d lambda by 2a. I just copied that here as a 2 came and remove it last. There is no 2 here because it's only n lambda by a. So d times of n lambda by a. So this is the explanation for the formation of the central maximum, secondary minima, and secondary maximum. Now this is the pattern roughly. This is a central maximum. This is called the first secondary minimum. This is a first secondary maximum. This is also first secondary maximum on the right side. Now this distance, or this the difference of the angular position. This is theta, lambda by a. If you put n equal to 1, you get first darkest lambda by a, first minimum. The central maximum ends with the first minimum. That's a lambda by a position, both left and right. So this spacing from minus lambda by a to plus lambda by a, that angle is called the angular width of the central maximum. So here to here is lambda by a, here to here is lambda by a. Total will be final position minus initial position. Lambda by a minus lambda by a will be lambda by a plus lambda by a will be 2 lambda by a. That's the angular width of central maximum. Now linear width you can just multiply with capital D. So it will be 2 times of d lambda by a. That's for the linear width of the central maximum. Now for secondary maxima, this is secondary maxima, the width will be between 2 minima on either side. So 2 lambda by a minus lambda by a will give you the width of the secondary maximum. So that will be again lambda by a. For secondary minimum, between one bright and the next bright. So the bright positions will be, if we give n equal to 1, this will be 3 lambda by 2a. If we give 2, 5 lambda by 2a. So the difference will be 5 lambda by 2a minus 3 lambda by 2a. It will be 2 lambda by 2 again lambda by a. So both secondary maxima and secondary minima are of same angular width. So to find the linear width, we can just multiply with capital D, will be d lambda by A. That's the width for both secondary minima and maxima in terms of linear width. There was a correction here. This is not 2A, it's only 10 d lambda by, because we multiply with lambda. I just copied from here. That's what happened.